Hello, in this video I'm going to give some background to James Watt. This is the chap that's got the unit of watts named after him. Now, this is our rate of transfer of energy, our joules per second. So, what did this guy do to get one of the big units of physics named after him? Right, so James Watt, he was a Scottish inventor, engineer and chemist. And he was active in the latter part of the 18th century and the early 19th century. He was, he was one of the main driving forces of the Industrial Revolution in Britain at that time. And although he did a lot of things, he's most famous for his work on steam engines. Now, when I'm talking about steam engines here, I don't mean trains. I mean engines that are powered by steam. Now, of course, that could be a train, but steam engines can be used for a lot of things. I mean, engines can be used for a lot of things. And back then, people wanted to operate all manner of different types of machinery and operate pumps and things like that. And steam engines were, really transformative in making these processes and pumping and engines and things so much more efficient, so much more practical to use, and so much more productive. So what did Watt actually do? Well, at the time, the engine that was being used was the Newcomen engine. This was the first widely used steam engine, which Thomas Newcomen invented in 1712. Now, in 1776, Watt came up with an improvement on the Newcomen design. Now, you can see this is over 60 years since the Newcomen engine was actually invented. So it had been, put to good use and had, great effect. But Watt managed to solve some of the numerous problems with the Newcomen engine. So let's look at what was going on with the Newcomen engine. So say you wanted to pump some stuff out of the ground. You got a hole in the ground and you're pumping some water out of it. You've got some water sitting in here and you drive down a big plunger, which is then going to force up water either up the same channel or a separate channel, something to drive this water up to the surface. So we need to keep driving this plunger in and out of the ground in order to get this water to come up. So you might have a design, some structures, much like the nodding donkey designs that you get in the US, where you have this weighted beam, which is heavier at the left end than it is at the right end here. This is attached to a supporting structure. And now we need to get this beam to keep going up and down. So if we can push down the right hand end, left hand end goes up, you let it go, and then the heavy end drops down, it drives the piston, the plunger into the ground. So this is what we're trying to do. If we can attach the right hand end to an engine to do all of this, then great, we've got a machine that can pump stuff. So this is great. Let's have a closer look at what's going on this right hand end then with the Newcomen engine. Right, so we attach this to a piston. So we've got a plunger going into a sealed column. So this is all sealed off. And we've got some space at the bottom here of the piston when the plunger is sitting at the top in this equilibrium position. So we need to get this plunger to go down into the piston, which will pull down the right end, pull up the left end, and allow us to start pumping stuff over here. So how are we going to get this piston to go downwards? Right, we need to connect the bottom area, this area at the bottom of the piston below the plunger, to two things. First of all, we've got what is essentially a big kettle on one side. This is where the steam is coming in. So we've got this kettle down here. It's filled with water, or part filled with water. We heat up the water, which is creating a whole load of steam. We got a valve here, and when we open the valve, all of this steam is going to come out and it's going to fill up inside the piston. Great, so that's filling this up with steam. Obviously the pressure is going up, so the pressure goes up, keeps the piston at the top. So we need to get a big pressure drop. And if we get a big pressure drop, then the piston will be driven down because we've got atmospheric pressure pushing down on outside. So if we can get low pressure inside the piston, then this plunger is going to get sucked down and it's going to pull down the right hand end of this bar. So how are we going to get this low pressure region? Well, we need to attach this part of the piston to something else. In this case, we have a water reservoir, which is also got a valve separating it and the piston. This is just filled up with water. This is cold water. There's no heating going on here. So when we open this valve connecting it to the water part, we're going to spray some water in to this area below at the bottom of the piston. That is going to condense the steam and create a vacuum or a near vacuum at the bottom of the piston, which is then going to suck this plunger down because we've now got low pressure inside. So all of that steam that was a gas, the water comes in, it cools it down, and it condenses it, and you get this sort of little layer of water at the bottom. So you just spray a small amount in, and then immediately close off the valve again. Sucks the piston down, lowers the right end here, lifts up the left end. You then open up this valve to put steam back in. The steam goes back in, piston goes back up, right end goes back up, and the plunger goes down into the ground over here. So we've got this continual process of fill up with steam, condense the steam, piston comes down, fill up with steam again, condense the steam, piston comes down. And that's how this steam engine is working. And this is great. I mean, the Newcomen engine could repeat this process maybe every 10 seconds, something like that. Maybe a little bit longer, but you might get 4, 5, 6 cycles a minute, something like that, which is a lot better than people had available to them before 1712 and the advent of this engine. But you can see one immediate inefficiency of this, that we're continually heating and cooling not just the gas, the steam that we've got inside the piston, but the whole piston itself. So we let the steam in, and you've got to do extra work because you've got to heat up all of the piston, and then the water comes in, it condenses the steam, but it also cools the piston, which we then need to reheat again. So not only are you using a whole load of energy that you don't really need to use in heating the piston and then cooling it and heating it and cooling it, but all that heating and cooling of the piston is also going to put it under greater stress, so it's going to wear out quicker. So what did with this was he set up a separate condenser. So rather than having the water going straight into the piston, he had his piston with the steam coming in, so that is unchanged. But now the condenser, this was a separate tube that went off to the condenser, which was then attached to the water. So when the valve was opened, so you've now closed the valve to the steam, we've got all the steam in here, you open up the valve to the condenser. The difference in pressure, because you've got high pressure in the piston, low pressure in the condenser, the steam is then pushed down this pipe into the condenser. You then spray the water in to the condenser to condense the steam, which creates an even lower pressure, which then creates low pressure in the piston with the same effect as before, but the piston still remains hot. The loss of the energy to the surrounding material is happening down here in the condenser. So there was a big energy saving in this, and what pretty much doubled the efficiency of these steam pumps, because you didn't have to keep on reheating the piston all of the time. So that was his sort of main breakthrough. There were a few other things he did with these engines, but I think that was the main one. He then teamed up with a guy called Matthew Boulton. That's Bolton with it's got a U in it. He was an industrialist, a sort of manufacturer based in the West Midlands in England. And Watt and Boulton teamed up together. Watt as the inventor and Boulton as the manufacturer, and they produced a whole load of these steam engines in what is now in Birmingham or near Birmingham at the time. This completely transformed and really turbocharged the Industrial Revolution in Britain at the time. As I said at the start, Watt did quite a few other things. He was a chemist. He developed various chlorine-based cleaning products, bleaching products, things like that, that were better than a lot of the things that were available at the time. So he did a lot of that work. He also made, weirdly enough, a portable copying machine for documents, and apparently people still use these things up into the early 20th century. He had this way of copying handwritten ink manuscripts. He had lots of ideas, and was quite the inventor extraordinaire over quite a load of different subjects. His partnership with Boulton and everything that went on. I mean, the West Midlands was a real hotbed for production and innovation during the Industrial Revolution, and the Watt and Boulton partnership, along with various other people who were active at the time, really was quite something. It was world changing. So there you go. That's a bit of background to Watt. I'll put some links down in the notes below if you want to look up any more about him, but at least you get a bit of a flavour of what he was doing and when.